Good morning everyone. Myself N.Uday Ranjan Goud, working as Assistant Professor in Department of Aeronautical Engineering, MLR Institute of Technology. So today we are going to have a session on the combined bending and in-plane loading. In the previous sessions, we have seen the thin plate subjected to bending, thin plates subjected to bending and twisting, and after that we have seen thin plates which are subjected to distributed transverse load. Now in this module we are going to see, along with bending, twisting and transverse load, we are going to see how it is going to affect the thin plate when combined all these loads along with in-plane loads are act. Now before that, first of all we have to see what are in-plane loads. So in-plane loads are nothing but the additional loads which are encountered on the aircraft surface. So apart from the bending, twisting and transverse loads. So these in-plane loads, if they are of less intensity, they may not affect the bending of the plate, but if the intensity of the in-plane loads are more, then they are going to affect the bending of the plate. So now in this module, we are going to see such a case of in-plane loads. Now, the combined bending and in-plane loading. The learning outcomes in this module are: students are able to analyze various boundary conditions of the edges, and students are able to determine the deflected form of the thin plate. Now, so additional in-plane tensile, compressive or shear loads, they'll produce stresses in the middle plane, and we know clearly that the neutral axis, about the neutral axis or neutral plane, then there exists no tension and no compression. So these additional in-plane loads, they produce stresses even in the middle plane as well, and these in-plane loads, if they are of sufficient magnitude, they are going to affect the bending of the plate. So therefore these in-plane stresses are very small when it is compared with the critical buckling stresses, and if the in-plane stresses are small, if they are not small, then they are going to affect the bending of the plate. So therefore these in-plane loads must be considered in the analysis of thin plate when they are subjected to loads. Now, so to start with this derivation, now let us consider one small element, and you can see the diagram here. So in this diagram you are able to see the two views. So one is the plan view and one is the front view, and so now in the front view the plate looks like this one, and in the top view the plate looks like this one. And let us consider XOZ axis system which is there here, and in the top view we can see XOY axis system and in-plane loads. So we'll designate these in-plane loads as NX, NY and NXY, where NX, NY and NXY are the direct and shear in-plane loads per unit length. So always we have to remember that the NX load is taken as NX per unit length. Similarly, NY is also taken as the in-plane load in y direction per unit length, and NXY is the shear load per unit length. So these are the in-plane load notations we'll give: capital NX, capital NY and capital NXY. Now let us try to understand the diagram first. So in this diagram, now let us assume that if you draw a tangent to the curvature of this edge, whatever we consider, let us assume dou W by dou X is the slope on which the NX tangential force is acting, and on the other hand we are going to take this with some increment. So that increment is nothing but dou W by dou X plus dou by dou X of dou W by dou X into delta X. And similarly the loads taken, if on the left hand side the load is NX, and the other edge also the load with increment NX plus dou NX by delta X into delta X. So NX is the load. Now we are going to see only in the front direction, so we are able to see only the NX load, that is acting tangential to the surface. So NX load with NX increment, and let us assume in the top view, and we can see clear, just like the principal stresses, we can see this clearly. NX is the load perpendicular to this surface, and NY is the load which is perpendicular to the horizontal surface, and NYX is the shear load, and you can see the NXY and NYX are equal in magnitude and opposite in direction. So that has been designated here. And similarly, now these NX, NY and NXY loads we have to represent on the edges opposite to it. with some incremental change. So Nx is the in-plane load per unit length and it is acting in x direction, and on the other hand with increment Nx plus dou Nx by dou x into delta x. Similarly, Ny which is acting upward, and now on the other edge opposite to it, it acts downwards and its increment is given by Ny plus dou Ny by dou y into delta y. Next, coming to the shear loads, Nxy shear load is acting tangential to the surface on the left edge, and on the other edge opposite to it, it is acting downwards and it is given by Nxy plus dou Nxy by dou x into delta x. Next, another one, Nyx is the shear load acting on the upper surface, and on the lower surface opposite to it, the incremental shear load is nothing but Nyx plus dou Nxy by dou y into delta y. So whatever the equations we are going to write, that we are going to write from this diagram only. So you have to draw this diagram and denote all the notations properly in such a way that it will become easy for us to write an equation, either it may be equilibrium equation or moment equation. Okay, so this is what the small element of elevation and plan view we have seen. So as we discussed, Nx, Ny and Nxy are nothing but they are shown in figure, and they denote direct and shear forces per unit length and which are produced by the in-plane loads. And since there are no resultant forces either in x direction or y direction from the transverse load, we need to include in-plane loads as shown in figure, because we are not considering the effect of any other loads. We are just considering the effect of in-plane loads alone. So there are no other forces are there in the diagram. So therefore, now we are considering the equilibrium of the element in this direction. So the first equilibrium direction what we are taking is considering the equilibrium of the element parallel to OX axis. Now if you go back and see, this is the OX axis. Now we are considering the force equilibrium parallel to this axis. Now when we take the parallel equilibrium parallel to OX axis, now you can see here Nx is the force. Now Nx is the force, and when you take the equilibrium parallel to x axis, and it is having some component here. So the angle is dou w by dou x. So it's going to give cos of the component. So I'm writing cos of dou w by dou x. So this is acting in left direction, so you can consider it as negative force. So the total force Nx into cos dou w by dou x. But here we have to remember the Nx is the force which is acting on which edge? The vertical edge. For the vertical edge, the length is delta y, whereas the horizontal length it isn't. So Nx is the force per unit length. So you have to multiply with the length which it is acting. So Nx into delta y, and then you have to take the cos of the component. So this is the force equilibrium with respect to Nx load that is acting in negative x direction. Similarly, if you try to write the force equilibrium due to this Nx plus dou Nx by delta x into delta x, and you can write plus Nx plus dou Nx by dou x into delta x is the force per unit length, and also it is acting on delta y edge, which we have to multiply, and then you have to write cos of the angle. So cos of the angle, what is that angle? This entire angle we have to write. So that is dou w by dou x plus dou by dou x of dou w by dou x into delta x. Okay. So after writing like this, what we have to do is we have to take the approximations for cos theta and sin theta. And from the mathematics, we know that the approximation of cos theta and sin theta. So cos theta can be approximated for very small angles. We can approximate it to 1, and sin theta we can approximate it to theta. So by taking this into consideration, here we have cos of the angle. So this we can remove and write by 1. Similarly, the cos of the angle here also there, that you can remove and replace it by 1. So that is what we are going to see. So these are the two forces. Just for example, I have taken these two forces which are parallel to OX axis. Like that, we have to inspect what are the other forces that are there in the parallel to OX axis, and then we have to take all that forces and write as an equilibrium. For example, what are the other forces are there? Now Nyx is there, which is parallel to OX axis, and Nyx increment is also there, which is parallel to x axis. So in addition to Nx and Nx increment, we have got Nyx and Nyx increment that are acting parallel to OX axis. So these are all to be taken into consideration while you write the equilibrium equation parallel to OX axis. So this is the equation which we have written. So nx plus dou nx by dou x into delta x into delta y, that you have to multiply the edge and then cos of the angle, minus nx delta y cos of the angle, that we have to take. And just we have seen that even the nyx also parallel to OX axis. So nyx increment, and it is acting on which edge? Delta x, and nyx with multiplying with the delta x edge. So this is the force equilibrium parallel to x axis. Now after that we use the approximations and we'll try to reduce this equation. Okay, so you can see here for small deflections, dou w by dou x and dou w by dou x plus dou square w by dou x square into delta x are small, and the cosines of these angles are therefore approximately equal to 1, that we have seen. And now the previous, this complete equilibrium equation is going to, here this and is going to cancel, and again nx also going to get cancelled here with nx term, and you left with the increments you have only very small angles. So therefore the equation now reduces to dou nx by dou x plus dou nyx by dou y, that is equal to 0. So this is the equilibrium equation which we have considered parallel to OX axis. Now in the similar case, you can consider the equilibrium in y direction also. So in the y direction, when you take the equilibrium equation in y direction, you can write in a similar manner. Like here we have dou nx by dou x, then the next one will be dou ny by dou y, and here we have dou nyx by dou y, then you can write it as dou nxy by dou x, that is equal to 0. So these are the two equations of equilibrium what we have for the in-plane loads. The next one what we have to see is, now we have considered the nx load and ny contribution we have written. Now we have to consider nxy load also. So nxy is nothing but the shear load. Nxy is additional shear load. Okay. So this, we know that again this nxy acts tangential to the surface, and again we have nxy on the other edge, nxy increment, and we have nyx edge, nyx load on one edge, and on the other edge we have nyx with increment. So these four also should be considered. But when we see the shear load, whenever a load that is acting parallel or tangential to the surface, then it is going to tilt. Okay, whenever the two parallel loads are tangential to x, and then it is going to tilt. So this position what you are seeing here is nothing but the tilted position when the shear load is applied on the edges of the plate. Now let us try to understand this diagram first. So this is the XOY plane that is taken, and let us assume that the plate is twisted or deflected by an amount of dou w by dou y, and on the other edge that increment, we are taking that angle with some increment. So that is nothing but dou w by dou y plus dou by dou x of dou w by dou y into delta x, and you can observe the edges lengths also, that is delta x and delta y. So now in this diagram we are just trying to take only the nxy, what is the nxy contribution for the additional load as in plane load for the plate. So now here we are just considering nxy. So nxy is the force shear load that is acting on edge and on this edge, and on the other edge opposite to it is nothing but nxy plus dou nxy by dou x into delta x. So this is the shear load that is acting on the other edge opposite to it. Okay, and now for this diagram we have to consider the equilibrium. Now from the figure, the component in z direction due to the nxy shear load is given by, so now the equilibrium is being considered in z direction. Where is z direction in this? We have x axis, y axis and origin here. So z axis is acting in the vertical downward direction. So now whatever the forces we have, shear loads nxy and nxy increment, that we have to take first. And for example, this nxy shear load is acting on this vertical edge on which the edge length is delta y. So first of all, nxy should be multiplied with this delta y so that it will become a shear load rather than shear force per unit length. So now after that you have to consider its component. Now for this one, now you have to take the component like this. So this will become cos of the component. When you try to take parallel to y-axis, is going to take cos of the component. So therefore, in the z direction is going to give sine of the component. So if you try to write this, you are going to write nxy into delta y is the shear load, and then you are going to write sine of dou w by dou y. Okay, so that is the component what we are going to write. Okay, that we are going to see now. So now here, and then sine of the component, like we have written sine dou w by dou y into nxy into delta y. So nxy into delta y, and sine theta can be approximated to theta, so that we can write sine dou w by dou y as simply dou w by dou y. So in the equation what you are going to see next, it is written directly. So first, which you can see here, nxy into delta y, and sine of dou w by dou y is written as dou w by dou y itself. Sine theta is approximated as theta. Similarly, and that we are considering in the negative direction, and the positive increment what we have, we are considering, try to considering, because z axis is vertically acting downwards. So all the downward components, let us assume that we'll take the positive signs, and then the loads which are opposite to this z, positive z direction, we can consider them as negative. So now nxy plus dou nxy by dou x into delta x is the load multiplied by this edge length, that is delta y, and then sine of this angle, that is written as angle itself. So that is written here, nxy plus dou nxy by dou x into delta y is multiplied, and then sine of this angle, now it is written as directly angle itself. Sine theta is approximated as theta, and then minus nxy plus minus nxy into delta y into dou w by dou y. Okay, so further it is reduced, and nxy one term can get cancelled with this one, and then our equation reduces to nxy dou square w by dou x dou y into delta x delta y plus dou nxy by dou x into dou w by dou y into delta x delta y. And you can neglect the higher order terms and write this equation. And similarly, so this is what you have nxy contribution. Similarly, we have nyx as well. So you have to write in the similar manner the nyx contribution also. The contribution of nyx is given by, just try to replace x and y terms. So nxy, here we have nyx dou square w by dou x dou y. So here you can write dou square w by dou y dou x, which again it is the same. Dou x dou y is same. Here we have dou nxy by dou x. So you can write dou nyx by dou y. Instead of dou w by dou y, you can write dou w by dou x and delta x delta y. So this is the nyx contribution for the thin plate. And now next, the components arising from the direct forces per unit length are readily obtained from the figure 1. So if you try to look out the, so this is the nxy contribution we have seen, and nyx contribution we have seen. Similarly, if you try to see the contribution of nx and ny, so these contributions can be readable directly from the figure itself. So let's try to look into that also. So this is the diagram which we have, original diagram. So nx contribution, nx with nx increment length, and ny contribution, ny and this one. So this can be written. So nx multiplied by its edge length, that is delta y, and nx increment also. This is dou nx plus dou nx by dou x into delta x with this increment. So that also can be taken as the contribution. Okay. So let's try to write this as an equation form. So then we can write it as nx plus dou nx by dou x into delta x, and it should be multiplied with the delta y edge. And then what you're seeing here is nothing but the sine of the component. Let's try to go back to the diagram and see and what we have here. So nx here, and here you can see nx in the top, in the front view you can see clearly. So nx plus dou nx by dou x is the force, and for which when you try to take along x axis, it's going to give as a component, and when you take in y axis, it's going to give sine of the component. So similarly here you can write the sine of the component. Earlier when you take equilibrium parallel to x axis, we took cos of the component. Now the equilibrium, it becomes what? Sine of the component. So with the and angle is nothing but this is the angle. So it will become sine theta as theta. So directly we'll write this as the angle. So now here we are going to write that one. So nx increment multiplying with the delta y edge and then the sign of the angle. Similarly, on the other edge opposite it, nx into delta y into dou w by dou x. And when you try to reduce the form of this equation, you are going to get nx into dou square w by dou x square into delta x delta y plus dou nx by dou x into dou w by dou x into delta x delta y. So this is the nx contribution. Similarly, you can write ny contribution also by interchanging the x and y terms. So you are going to write ny dou square w by dou x square. In place of that, you can write dou square w by dou y square, delta x delta y common. Here also delta x delta y is common. Dou nx by dou x, you can write dou ny by dou y. Dou w by dou x, you can write dou w by dou y, and you can write the ny contribution as well. Okay. So now we are going to add all the contribution. So earlier we have got nxy contribution. You can consider this as first equation, and this is the ny x contribution. You can consider it as second equation, and then you can write nx contribution as third equation and ny contribution as fourth equation. Now all these 1, 2, 3, 4 equations are added together so that for a plate which is supported by the shear loads, that is nx, ny, nyx and nxy. So all these contributions can be written as a single equation, and you are going to get this equation when you join all this 1, 2, 3, 4. And again, using the equilibrium equations in x and y, and we'll try to reduce that form of the equation as nx into dou square w by dou x square plus ny into dou square w by dou y square plus 2nxy into dou square w by dou x dou y into delta x delta y. So this is the contribution of the in-plane loads. So these are the in-plane load contribution which are added to the bending, shear and torsional loads which are already existing. So this we have studied individually separately, but in the analysis we have to add this in-load contribution to the other types of loads also. Okay. So when you try to add this, the governing differential equation for a thin plate which is supported by transverse loads and in-plane loads is given by dou power 4 w by dou x power 4 plus 2 into dou power 4 w by dou x square dou y square plus dou power 4 w by dou y power 4, that is equals to 1 by d. Earlier we had just q by d. Now since this q is a transverse load, now you have to add the in-plane load contribution to the q only. So 1 by d of q plus nx into dou square w by dou x square plus 2nxy into dou square w by dou x dou y plus ny into dou square w by dou y square. So this equation is very important equation, because it's going to give the differential equation, governing differential equation for a thin plate which supports transverse loads as well as in-plane loads. Okay. So for the problems, if the in-plane loads are not given in the analysis, so you can straight away take all this as 0, and then the existing governing differential equation, straight away you are going to get it as q by d. Okay. But if the in-plane loads are given, so you have to take these into consideration. So this is the in-plane load effect what we have. So the governing differential equation also you can see here. And then when it comes to the bending of thin plates with small initial curvature, now in the thin plates, if you have small initial curvature, what do we do is, first of all we take that initial curvature as w0, and then the final, for example it is deflected by some amount, then we will consider it as w1. So the total deflection will be equals to w. So we write w equals to w0 plus w1, where w0 is the initial deflection and w1 is the change in deflection, and the final deflection will be w. So what is that equation that will change when the initial curvature is present? So when the initial curvature is present, the left hand side of the obtained left hand side equation what we have, which is clearly for bending moments, and it depends on the curvature of the equation. You can see clearly w is nothing but the deflection, or 1 by w, that is curvature. So this left side of this equation completely depends on the bending moments. So therefore in the left side of the equation, instead of w, since w1 is the actual deflection, w should be replaced by w1. So the left side of the equation you can see that is written in terms of w1 instead of w. Whereas in the right side of this equation, in place of w, the total deflection is to be used, that is W0 plus W1. So right side is because of the initial deflection and the change in deflection. So we have to write the final deflection. So just try to modify this equation. In place of W, we are going to write W0 plus W1. So this is nothing but the effect of initial curvature on the deflection, and therefore it is equivalent to the application of the transverse load, and whose intensity is given by transverse load, that is Nx into dou square W0 by dou x square plus Ny into dou square W0 by dou y square plus 2nxy into dou square W0 by dou x dou y. Okay, and in which you can assume the initial form of the deflected plate as W0 equals to summation m equals to 1 to infinity, n equals to 1 to infinity, amn sin m pi x by a sin n pi y by b. You can consider this deflected form of the plate, and you can substitute in this equation whenever you have bending of thin plates with small initial curvature. And therefore, when you substitute all these loads for nx and everything, and if W0 is given as amn sin m pi x by a sin n pi y by b, then the change in deflection, that is W1, is taken as Bmn, another coefficient, unknown coefficient, that is Bmn sin m pi x by a sin n pi y by b, where Bmn is equals to Amn into Nx divided by pi square d by a square into m plus n square a square by mb square whole square minus Nx. This we have already seen in the previous classes also. Okay, so Bmn is equals to, in terms of, we are writing in terms of Amn and the Nx compressive load. So this is, and whenever you have the bending of thin plate with small initial curvature, you have to calculate this unknown coefficient Bmn and substitute over here. You are going to get the actual deflection for the thin plate with initial curvature. Okay, so this is about the bending, combined bending and in-plane loads, and the bending of thin plates with small initial curvature. So thank you everyone for watching this, and in the next we are going to see the strain energy subjected to bending and twisting.